Okay, so this video lecture is going to get on into reaction mechanisms, which is super fun. And this is going to kind of explain why some reactants don't affect the rate. And so let's take a look. So even though a balanced chemical equation does show the result, okay, of a reaction, it may actually occur in a series of steps. And so that's what a reaction mechanism is, okay? And it can be thought of as like the pathway. And each step is known as an elementary reaction for vocab there. So an elementary reaction, so a step in the overall reaction, is actually showing the actual particle collision that takes place. And so if that's true, we can actually write the rate law for that reaction, and it would match the stoichiometry because that is what's actually occurring molecularly. And that's different than the overall reaction that you'll see. Okay, so if the actual elementary reaction, if it's labeled as elementary reaction, then it's actually showing the particles that are changing. And so here we would say, oh, that 2 on the A is going to, for every 2A, that's going to quadruple the rate. It's going to change the rate. And then for every 1B, that's going to double the rate. So the other kind of vocab thing, so if you have an elementary reaction, if it says elementary, then yes, you can write the rate law directly off of that. Molecularity is how you kind of talk about how many things are colliding. So what this is saying is that 2 A's and 1 B have to all collide at the same time and form 1 C. Okay, so if a reaction is elementary, then we refer to its overall order as its molecularity. And that would represent the number of particles that would have to collide with the right orientation and high enough energy to successfully form the product. So if you assume all of these reactions are elementary, then this is how you would label the molecularity. So if A is turning into a different thing, you call it unimolecular. If you have 2 things coming together, 2 different things, they collide, it's called bimolecular. It can be 2 of the same thing, that would also be bimolecular. And if you had 2 of one thing and 1 of another, or 3 different things all colliding, basically 3 things, call it termolecular. And as you can probably imagine, termolecular elementary reactions are really very rare, which is why usually a chemical reaction that has like multiple things in high coefficients is not what's happening. It's not happening all in one step. So if it asks you, like, what is the molecularity of a reaction, you just look at how many things are on the reactant side: 1, 2, 3, unimolecular, bimolecular, termolecular. So we have said that rate laws have to be determined experimentally, and that's because we can't assume that a reaction is elementary, because there could be a mechanism behind the scene. But if your overall reaction is termolecular, it's probably a good sign that there is a mechanism at work. And again, just emphasizing that because an elementary reaction does represent a single collision, we can use it to write a rate law. So breaking this down. So this reaction, and mechanisms are difficult to determine, but that's what, like, a lot of chemists, that's their job, is to determine the reaction mechanism. So here we have the step 1 is this NO2Cl molecule, and it's forming NO2 and Cl. And then step 2 is the NO2Cl molecule with chlorine forming NO2 and Cl2. So these are kind of like 2 different reactions. If we write the overall equation, we can add them up just kind of like we did with Hess's law and get the overall. So we've got 2 on the reactant side of these NO2Cl molecules. And then, well, if we do the whole thing, so NO2Cl, 2 of them, plus we have chlorine. And then on the product side, we have 2 NO2s, a Cl, and a Cl2. And that's where you can see that the chlorine atom there is on both sides, just so like in Hess's law, they would cancel. So that's why it's not in this one. But what this shows, okay, so the overall reaction shows these 2 NO2Cl molecules, and it looks like they're colliding, that it would be a bimolecular reaction. But it's It's actually, the mechanism proposes that there's no collision between the NO2 Cl molecules of what actually makes the NO2. And so that's where the rate law would not be NO2Cl squared, because that's not what is happening behind the scenes. So let's look at this a little bit more. All right, so we call the chlorine that got canceled. So it was made, and then in step 2, it was consumed. Okay, that's an example of intermediate. It's made in one step and then consumed in another, so it cancels from the overall. So that's what an intermediate is called. If something is made in one step and then consumed in another, it's considered an intermediate. Sometimes not all components, but not all components that cancel are intermediates. It's only if something is made and then consumed. Okay, but if a component is consumed as a reactant but then regenerated as a product in a later step, we call that a catalyst. So a lot of you have been asking, like, what is a catalyst? It can be a behind the scene mechanism. So the presence of a catalyst affects the mechanism by usually lowering the activation energy, or it can increase the frequency factor. Like, it can create more successful collisions, and I'll show you a little bit more here. So in this reaction mechanism, it's showing 2 NOs and 2 N2Os forming in this elementary step. And then the NO2 is being made again as a product in the second one. So if we wrote the overall, okay, the overall, these cancel and these cancel. And then you can also see this NO2, 2NO2 here, those are intermediates. The overall, the stuff that doesn't cancel, are the 2 dinitrogen monoxides forming the nitrogen and the oxygen gas. So the NO would be considered a catalyst, and the NO2 would be considered an intermediate. And so a catalyst can be something that, like, we don't write in the overall reaction. So this is how we've written chemical reactions, because what's actually changing chemically is the dinitrogen monoxide, and it's forming nitrogen gas and oxygen gas. But how we got there wasn't just these 2 molecules colliding and then forming the nitrogen and oxygen. It's actually a catalyst here is colliding, forming the nitrogen and the nitrogen dioxide, and then that nitrogen dioxide is then colliding with itself, reforming the catalyst. So that's where I say a catalyst, it may undergo a chemical reaction, but it comes back, it gets spit out at the end. So that's why we don't write it in the overall chemical reaction. And then just FYI, an inhibitor would be similar. Like, we assume that stuff that is consumed and then spit out at the end is a catalyst, but sometimes you can put something, at the beginning of the reaction that slows it down. It works the same way, but just FYI. So that would have like a negative effect on the reaction rate. So just a little bit more different types of catalysts. Okay, so limitations of catalysts. So even though the catalyst can be regenerated and doesn't get consumed, it can still be limited. And if the catalyst is part of the rate law, then its concentration does affect the rate. If it isn't, then it doesn't affect the rate. So catalysts can be different things. So they can be a solid surface, like this is what this example is shown. And so this is why catalysts may or may not affect the rate. Because if all of the sites on the metal surface are taken, then it can only increase the rate as much space as it has. And so this is showing that this hydrogen molecule and this C2H4, this ethene molecule, are hitting this nickel surface, okay? And it serves as kind of a holding place for these molecules to kind of meet each other. And so then these kind of stick to the surface, give them a higher chance of meeting and rearranging. And you can see then they're showing the actual mechanism of the hydrogen sticking to the nickel and the double bond sticking to the nickel, and that then these hydrogens kind of then form in these places, and you're forming the ethane molecule. And it's being held by intermolecular forces. But if all of the surface of nickel is covered in these, then you can't, it will increase the rate, but it won't increase it maybe infinitely. So that's a model for a catalyst. Okay, so this is another example showing, there are these oxygen atoms that are kind of stuck on this surface, and they allow other things to kind of collide. And so if you have this CO molecule that then can come and hit one of the oxygens that's stuck, you can then form the CO2 there. Sometimes in biology, they show these kind of images for an enzyme catalyst. This is what happens in your body a whole lot. Very simplified version, of course, but you have some, they call it a substrate, but it's some molecule, and it then the catalyst allows a place that allows, in this case, this bond to be broken between this molecule and then break it into two pieces. And so again, the catalyst will increase the rate most likely because it's lowering the activation energy, so then more of these molecules can then form the product, and it's holding it there that then just allows more success to happen. Sometimes here, this is just showing one in a chemical reaction. You can kind of determine if something is an intermediate or a catalyst looking at the overall mechanism here. So this one is showing the hydrogen peroxide with an iodine molecule, and the iodine molecule is here as a reactant and it's here as a product. And then you can see this IO, this hypoiodite here, and then those would be intermediates, because they're made and then consumed. And the overall reaction shows two of the hydrogen peroxides forming two waters and the oxygen gas. So a catalyst can be put in. It does change the reaction mechanism rather than just being hydrogen peroxide decomposing, which it will, but it just not a lot of it will at room temperature. This one is just showing a different one. So here you have the iron, and it's iron 2. So the iron 2 is a catalyst. The iron 3 would be an intermediate. And this H2, it'll get canceled there. It won't show up the overall. So it has to be added at some step, and then it's reproduced. So that would be like another catalyst there for the overall reaction. Yeah, so it just shows you different mechanisms and what a catalyst can and cannot do. So for this, you might be asked to determine the overall equation, identify any catalysts or intermediates. So we'll just add it up kind of like we did Hess's law. So the overall, you've got 2 NOs and lots of nitrogens, oxygens, so just make sure you write them carefully. And you've got 2 N2Os and 2 NO2s on the reactant side. The product side, you've got 2 NO2s, 2 N2s, 2 NOs, and an oxygen. And we can look at what cancels. So we've got the 2 NOs on both sides. They're going to go away. NO2s, they're going to go away. And the only thing, the overall reaction is this one. So that would be the overall. And then you can look back at the mechanism to see, okay, this was started and then got reproduced. So that's a catalyst. And this, NO2, was made, but then consumed. So that's an intermediate. And there you go. So let's also look at mechanisms and rate, okay? So the overall rate of a mechanism is determined actually by the slowest step. So one of those steps is going to be faster than the other ones, okay? So like this little thing, it doesn't matter how much sand or water or whatever you put in this step is going to determine the flow rate, okay? You can only go as fast as the slowest part of the mechanism. Okay, and it doesn't matter if the slow step is the first or last, but it will determine actually how fast the reaction proceeds. So it doesn't matter. This is why sometimes a reactant doesn't affect the rate, because it's not part of the rate limiting step. Okay, so you have to be given information about this. But if we are told that step one of this reaction is the slow step, then the rate law and the rate of reaction is dependent on that. So that is where the rate would be equal to, the rate law would be K times it's just the NO2Cl, just 1 raised to the first power, because that's the elementary reaction that determined the rate. So this is where the overall, you can see that because it's not actually 2 of those molecules colliding, so if you doubled the concentration, you wouldn't see a quadruple of the rate, you'd see a doubling of the rate. And that's because the first step is the rate limiting step, or the slow step. So you can write a rate law, like we could write the rate law for the second one, but it won't affect the overall rate because it's the fast step. So really the rate only depends on this. So that would be the rate law for the overall reaction for this. Yep, so if it's an elementary step, you can write the rate law based on the coefficients, but only if you're told it's an elementary step. So let's do this one. We have the proposed mechanism. We're going to write the rate law and the overall equation. So the slow step's the first one. We're going to talk about what if it's not. But if it's the first one, then the rate law is going to be rate is equal to K. And we've got 2 NO2s. So we can just write it as NO2 to the second power. There. You could write NO2 and then NO2 to the first, and it would combine and make it to the second. So that would be the rate law. The overall reaction that takes place, so here is an intermediate. It's not going to be included. It's going to cancel. And one of these is going to cancel. So I'm only going to write what doesn't. So really we have NO2 and carbon monoxide, sorry, not carbon dioxide. And they are forming nitrogen monoxide and carbon dioxide. They're flipping. That would be the overall equation, but the rate is based on that, which does not show the coefficients, and it shows that the carbon monoxide doesn't determine the rate at all. It's part of the fast step. So what if the slow step is in the first step? Okay, so like in this picture, right? You put a whole bunch of stuff in, but it's really the second or third step. So a rate law, though, can only be expressed in terms of reactants and catalysts. Intermediates can't be in the rate law because their concentration does not accumulate. As soon as it's made, it's then consumed. So if the rate determining step is not first, it may include an intermediate that will need to be substituted. So just showing you what you have to do if it's a substitution situation here. So you have to know what the overall reaction is. Experimentally, the rate law has been determined to be K times NO2 squared and H2 to the first, which doesn't match the coefficients, okay? And the proposed mechanism here shows 2 nitrogen monoxides forming this N2O2. This is said to be fast, and it's at equilibrium, which we're going to get into here, but let's introduce it. So basically, at equilibrium, the forward and the reverse rates are equal. So you're going to see how that comes into play here in just a second. The second one is the slow step. And so the rate for this one, we're going to write this one out. We don't care about the fast because it comes after it. But we can't, if we write the rate for the second one, it would be N2O2. Sorry, forgot the K there. And H2. Well, N2O2 is an intermediate. So this cannot be in the overall rate law. Plus, we already know what the rate law should be. Here, I'm going to show you how we got to that from understanding that this is the slow step. Okay, meaning we didn't need this to get there. But we're going to have to substitute out the N2O2. And maybe you can kind of already see it, but that the N2O2 would be, the rate of that would be equal to N2 squared. And then if we substitute it, that's where we're going to get that NO squared. But just to walk you through that. So again, the experimental has been determined to be this. So based on the slow step, we just wrote the N2O2. N2O2 is an intermediate. So we're going to use the equilibrium step and do a substitution because at equilibrium, the forward and reverse rates are equal. So what does that look like? So for the slow step, the rate would be the NO squared, and the rate reverse would be K to the -1 of the N2O2, which is what we're trying to substitute. So we set those equal to each other, and then you rearrange it, and you get that the N2O2 is equal to the K, which is the forward and reverse over each other, is equal to the NO squared. We're just solving for this so that we can then substitute it into the rate law expression, which, again, you can follow all of this. Usually, it's actually, I think, just simpler to see the substitution and put it in. But we're going to then substitute this N2O2 here with this. And you're going to get a whole bunch of Ks, okay, which you don't need to necessarily, but it's going to be some rate constant, but it's the relative rates of the equilibrium step and the slow step all combined. And then we plugged in the NO squared, substituted it for this. But all of those K values can be expressed as one overall K, which has to be determined experimentally anyway. So that's where you get the rate is K times the NO squared and the H2, which does match the experimental one. You have to do a little substitution. I think you can see it, and just plug it in if you had to do one of those. Let's do one, okay, which we don't have the answer for. All right, so we have the, let's write the overall reaction. So the overall reaction, this is an intermediate. It's going to cancel on both sides and the rest of the stuff. So the overall is 2NO plus Cl2 forming 2NoCl. And let's write the rate for each one. So this step is going to determine the rate, okay? But so this is the one we just have to then substitute back, because we won't be able to include the NoCl2 since it's an intermediate and it's the NO. So that's the rate of this one. This top one, okay, the rate forward, so rate F is the NO and the Cl2, and the rate reverse is just the NoCl2. Because the rates would have to be equal, we can substitute. So we can substitute this with these two. And so what we're actually going to get, if we then plug those in to here, we're going to get the rate law is going to be the NO, we've got two of them, squared times the Cl2. That it does happen to match the coefficients of the overall, but again, happen chance. Just getting rid of that NoCl2 for what the equilibrium reaction was. We got two of them, so that's what it ends up being for this. So other questions that could be asked. So here we've got the rate law for this reaction has been determined experimentally to be the NO2 and the F2. You can ask yourself, is this reaction mechanism elementary, or is there a mechanism? And how can you tell? Well, you look, so this is 1 and 1, and you can tell if it's elementary if it matches the coefficients. It does not. So what this means is that there is a mechanism at play, and you can tell because, well, it doesn't match the coefficients. If an elementary reaction has to match the coefficients, and sometimes it does match the coefficients, but it's still not, that's not the mechanism. I wouldn't give you anything like that, but that is something else that can happen there. Another way of wording that is, it's not elementary because the rate doesn't match the stoichiometry. And remember that actual term molecularity is really rare. So it's unlikely that the three molecules are all coming together and colliding. So you can also see this in an energy diagram. And so the energy diagram, if it's a mechanism, is going to have multiple peaks because each step is going to have a different activation energy, okay? And so each elementary step of the mechanism, it describes a complex, a collision with an activated complex and the activation energy. And then each one shows the relative activation energy. So there's a couple questions that could be asked from this. So how many elementary reactions are in the mechanism? So you're starting here, you've got 1 peak, 2 peaks, 3 peaks. So there's got to be 3 steps, okay? Each step has a different, oh, I want to do this last one. Peak is right there. The rate limiting step is going to be the one that has the highest amount of change in activation energy. So from the bottom of the peak, like so from A to the top before you get to B, from B to the top before you get to C, from C to the top before you get to D. So there's 3 elementary reactions. The rate limiting step is going to be B, from the second step of the mechanism. So A to B is less than B to C, and then C to D is the slowest. And then is the overall reaction endothermic or exothermic, because we don't care about the pathway, but rather the overall change, and the products are sitting higher than the reactants, so this would be endothermic. So now we would probably draw the reaction like this, you know, like with 1, but that might not be the actual mechanism that is at play there. So just some different things that could be asked. Here's another one. How many steps are in this mechanism? You've got 1, 2, 3 steps. It can also ask which one is the slow step. That would be going from the COCl to the COCl2, this second to the third, and this would be an exothermic reaction. So just some different things, and it's showing you the overall delta H, even though this third step is definitely the rate limiting step, and the one with the most activation energy. We did the iodine clock reaction, and this just shows you the proposed mechanism, which you can see there are some intermediates and a catalyst and all that good stuff. So this is a little bit more on reaction mechanisms. Hope you learned some stuff and asked your questions.